Hello everyone, I am Sebastián Marino and today I want to show you what we know about the radial structure of exoKuiper belts or debris disks and how this connects with the presence of Neptune analogues. You are all familiar with this figure showing in colored dots the mass and semi-major axis of known exoplanets. In black, you can see solar system planets. What I find very troubling is that we know very little about the population of low-mass planets at tens of AU. At the same time, over the last few years, thanks to ALMA, we have learned that while planetary systems are still forming, those outer regions are full of substructure in protoplanetary disks. That substructure has been interpreted as caused by planets by multiple studies. For example, in that figure on the right by Bai et al., you can see in colored dots what would be the mass and semi-major axis of those planets. They are typically Neptune to Jupiter mass planets at tens of AU. However, as shown by Lodato and Dugu, those planets are expected to continue growing, becoming gas giants, and possibly migrating inwards to end up at a few AU. The good news is that there is a different way to probe the outer regions. Planetary systems are not only composed of planets, but they are also composed of planetesimal belts, which are analogous to the asteroid and Kuiper belts. Collisions between planetesimals in those belts give rise to high dust levels, which are much easier to detect and image compared to exoplanets. In fact, we find high dust levels around 30% of AFGK stars. Therefore, we can use the structure of exoKuiper belts at tens of AU to learn something about the exoplanet population at tens of AU too. The structure of these belts is actually very sensitive even to low-mass planets. So what have we learned so far about the structure of those belts? Thanks to ALMA, we have been able to image more than 60 exoKuiper belts. This is a gallery of many of those disks, some of which form part of a big survey called Reasons that is being led by Luca Madra. It really shows the diversity of structures that we find, with some very narrow rings, with some very wide disks, some of them eccentric or asymmetric. One of the first things that we found is that disks are overall larger around more massive and luminous stars. In the figure on the right, you can see that the disk radius scales with stellar luminosity. The origin of this relation is still unclear, but it could have to do with the timescale of planet formation. For example, the radius of debris disks could reveal the radius beyond which the growing timescales were way too long, and those planetesimals did not grow further. Also, bear in mind that the error bars in this figure represent the width of those belts, and not the uncertainty on the disk radius. From the ALMA data, we have also learned what is the width distribution of exoKuiper belts. This histogram shows the distribution of the fractional width, which is the real width over the central radius. We find that narrow belts like Fomalhaut or HR4796 are not common, and these should not be used as archetypical debris disks. In fact, most belts are much wider, even wider than the Kuiper belt, shown here with a green line. Belts like Beta Peak or around HD 161868 are true examples of how wide exoKuiper belts can be. It is also interesting to compare the width distribution with the distribution of widths of rings in protoplanetary disks, that here are overlaid in orange. We find that most exoKuiper belts are much wider, and thus planetesimal belts cannot simply be formed in those narrow rings in protoplanetary disks. Some additional ingredient is really missing. Alternatively, maybe these white belts are made of multiple rings which we have not been able to resolve yet. So, over the last 3 years, I have studied the structure of these white belts, focusing specifically in 3 solar-type stars. Imaging 3 disks with ALMA, I found that these white disks were actually split into 2 by a gap, which is better seen in radial profiles of the azimuthally average emission. The 3 disks have gaps at about 70 AU, whose origin is still unclear. What is very interesting though is that together with HD 15115 and AUMIC, which also have evidence of gaps, we find that gaps are present in 5 out of 6 disks that we have been able to image with ALMA at sufficient resolution and sensitivity. This means that substructure seems to be common among debris disks as well. So if we interpret these gaps as caused by planets clearing their orbits from debris, we can constrain their masses based on the gap width. If we place them in this plot of known exoplanets and solar system planets, these putative planets would be located here. Such Neptune analogues will be actually detectable with upcoming instruments on JWST, the ELTs. So this sample of gapped systems will be really important to test these upcoming instruments and see if we can really detect these low mass planets. I want to focus now on the third system that I studied, that is HD 206893. This system is truly interesting. It has a brown dwarf at 11 AU discovered by Milieto. Its star shows a long RV trend that suggests an inner companion, and also the system has a proper motion anomaly that could confirm this inner companion. We imaged this disk with ALMA, and you can see the image on the top right, and maybe it's a bit blobby, but you can see that there is a decrement of emission between the star at the center and the bright ring further out. But if you see an azimuthally average profile, which is shown here on the bottom right, you see that the disk emission peaks at about 40 AU, and then there is a gap at about 70 AU. We find that the width of this gap is basically consistent with a planet mass of 0.4 Jupiter masses up to something like 4 Jupiter masses. What was unique of this study was that we could use the orientation of the disk as a prior to basically constrain the orbit of the brown dwarf. And we can do this because through secular interactions, we expect that the orbit of the brown dwarf should be aligned with the orbit of the disk. By doing so, we find that the brown dwarf is actually on an eccentric orbit with an eccentricity of 0.14, which could be confirmed actually with further astrometry. Finally, we can place all the constraints on this system in a single figure of companion mass versus semi-major axis. First, the error bar at the center shows the brown dwarf discovered with sphere. The same observations rule out the presence of a similar mass planet beyond 7 AU, which is represented in red in this figure. The ALMA observations constrained the disk structure, which revealed a gap and thus a putative planet at about 70 AU, and rule out also the presence of another planet in the green region, otherwise the disk would be disrupted. From dynamical arguments, we also know that there should not be another companion above the black dashed line, otherwise the system will be unstable. Then, HARPS revealed an RV trend imposing a lower limit also on the period or semi-major axis of an additional inner perturber, and a lower limit on its mass represented by the orange region. Thus, this inner companion should lie in this white triangle. Interestingly, the system has a significant proper motion anomaly when combining Hipparcos and Gaia data, and in order to explain it, we need the presence of a companion along this blue line. Although this blue line intersects the mass of this brown dwarf at 10 AU, we know that the position of this brown dwarf, the position angle, is inconsistent with the direction of this proper motion anomaly. So we really need the existence of an additional companion. What is interesting is that this blue line intersects with the white triangle where this companion creating an RV trend should be. So it is very likely that both RV trend and proper motion anomaly are explained by a single inner companion with a mass between 10 and 100 Jupiter masses and a semi-major axis of 1.4 to 2.7 AU. So to summarize in some stay-home messages, I tried to convince you that exoKuiper belts provide a complementary view of planetary systems. ExoKuiper belts are much wider than we thought in the past and than rings in protoplanetary disks. It seems that gaps are common also in white exoKuiper belts, The width of these gaps are consistent with Neptune analogues formed at tenths of a U. Finally, by imaging the disk around HD 206893, we were able to improve the orbital constraints on the brown dwarf, actually finding that the brown dwarf is likely on an eccentric orbit. We also found a gap at about 70 AU, which could be explained by a 0.8 Jupiter mass planets. And finally, the presence of 3 companions and a disk in this system really make this system an ideal laboratory to study interactions. And with that, I want to thank you for your attention, and I'm happy to answer any questions. Thank you.